here's our system of equations. We've got 1x plus 4y minus 3z equals negative 13, 6x plus 6y minus 3z equals 6, 5x plus y plus z equals 2. So our goal here is to try and find values of x, y, and z, ideally just one value of each that works for all three equations at once. Or maybe there's no values that make this work, or maybe there's many values that make this work. We don't know yet. We could solve this using techniques from standard high school algebra, maybe solving an equation for a variable and plugging it into another one, the substitution method, or the elimination method, adding an equation to another equation, maybe multiplying them by something first to get something to cancel out. There's several matrix approaches that streamline this process quite a bit though. One way is to set up an augmented matrix, augmented in the sense of enhanced by or increased by. We just write down all of the coefficients without worrying about the variables. So for instance, the first equation, 1x plus 4y plus negative 3z, we're just going to write it as 1, 4, negative 3 equals negative 13. Second equation, 6x plus 6y minus 3z equals 6. So we just copy all the coefficients in that order. And likewise, 5, 1, 1 equals 2. Usually with a vertical bar here to separate the coefficients and the numbers on the other side of the equal sign. But the vertical bar doesn't really have any mathematical significance. It's just a notation placeholder. The main idea is that instead of using written letters to keep track of the variables, we're using position to keep track of which numbers are coefficients to which variables. So this, for instance, is the column of x coefficients, the columns of coefficients on y, the column of coefficients on z, and the column of numbers from the other side of the equation. So each column represents a specific type of coefficient. Each row represents an equation. Any questions on that notation so far? So this would be called the augmented matrix, representing the system of equations. And in this context, augmented means we've taken a coefficient matrix and we've attached or augmented one more column. So augmented basically just means we're attaching two matrices or a matrix and a single column together. And then what we want to do is row reduce this in the sense of combining rows, doing certain operations on rows to make this simpler so we can get it to something that looks like an actual answer. And the operations we're allowed to do here are basically exactly what we would do with the individual equations. For instance, if you're solving this system of equations by high school method elimination, what are some operations you can do with the equations to combine them and get more information? Like, what would you do if you're solving this system of equations using high school algebra approach? For example, let's say you wanted to eliminate the 6x in this equation. How could you get rid of that 6x?
You can subtract the first and third equations from the second one.
Yeah, maybe you could subtract an equation from another equation or add an equation to another equation. In the context of the matrix, we'd be doing something almost identical, except instead of thinking of them in terms of equations, we're looking at them in terms of rows. So you can add everything in one row to everything in another row, one component at a time. For instance, we could add the 1 to the 6, replacing the 6. We could add the 4 to the 6 and turn this into 10. Add the negative 3 to negative 3, turn that into negative 6. Add the negative 13 to the 6, turn that into negative 7. So basically overwriting one of the rows by adding another row to it. Of course, just doing that alone wouldn't be very useful. Unless there's already something that's going to cancel out. But you can also add a multiple of a row to another row. In the same context that, for instance, we could cancel out this 6x by subtracting x and subtracting 5x. But we could also instead do that in one step by subtracting 6 times the entire first equation. Because that way, negative 6 times x would be negative 6x, which would cancel out the 6x here. And so the equivalent of that in matrix form would be adding a multiple of a row to another row. So for instance, we could add a multiple of row 1 to row 2. Doesn't even have to be a whole number multiple. Any scalar times a row and add that to another row. And likewise, you can also do just part of that. You can just multiply a row by a scalar. Like if this is a 5 and you'd like it to be a 1, you could multiply this entire row by 1/5, turning the 5 into a 1, and then 1/5, 1/5, 2/5. So those are the operations you can do. You can multiply a row by a scalar. You can add a multiple of a row to another row. And also, since the order didn't really matter here, like we could have written these three equations in a different order, you're also able to swap rows or rearrange the rows. So you can rearrange rows however you want. You can add a row to another row or add a multiple of a row to another row. And you can multiply any row by a scalar. As long as the scalar is not 0. If you multiply everything in a row by 0, you're losing information. You don't want to lose information. So multiply a row by a non-zero scalar. And there's many ways to go about doing this. There's like you can add any row to any other row, multiply any row by any scalar you want other than 0. But there's a useful result we want to get to. Our intended goal. What do we want to make this look like? What's our end goal here?
An upper triangle?
Yeah, upper triangle, and even better than upper triangle, if we want x equals some number, y equals some number, z equals some number, what would these three final equations look like in matrix form? If you just have x equals something, what would that look like as a row of the matrix?
I'm not sure, identity?
Yeah, we'd end up with the identity matrix. Because if you think of this in terms of x, y, and z, we've got one x, but we have no y and no z. So we'd write that as 1, 0, 0. 1x, no y, and no z equals some number. Likewise, this equation, we've got no x, 1y, and no z. So that's 0x plus 1y plus 0z equals some number. And then third equation, we've got no x and no y, just 0x plus 0y plus 1z equals some number. So when you're solving a system of equations using an augmented matrix, your goal is to row reduce it to the identity matrix if possible. It's not always possible to turn it into the identity matrix. If it is, if you can turn this into the identity matrix, then these numbers are the values of x, y, and z. So that means you'd have that solution, and that's your only solution. If you can't turn this into the identity matrix, if it's not possible to row reduce to the identity matrix, then that either means there's no solution or there's infinitely many solutions. But you can tell which that is by looking at why it doesn't turn into the identity matrix, what exactly is going wrong there. But you can still at least turn it into reduced row echelon form, which is basically as close as you can get to the identity matrix. So let's try this. Let's see if we can turn this into the identity matrix. The main things we want to look for, we want to take the idea of, have you seen the idea of a pivot yet? What exactly is a pivot?
It's the elements that are in the main diagonal.
In the end, it is in the main diagonal if we can get it to the form of the identity matrix. But they won't always have to be on the main diagonal. They might end up being somewhere else. The pivot is defined as you're going from left to right, the pivot is the first non-zero you encounter in the row. So as you go from left to right, you hit a non-zero here. Next row, you go from left to right, there's a non-zero, the first non-zero number, so that's the next pivot. Next row, you go from left to right, here's the first non-zero number you encounter. So that's what a pivot is defined as. The pivot means the first non-zero number you encounter in the row as you read from left to right. So the idea is to be in what we call reduced row echelon form, our goal here, you have to have every pivot be alone in its column. So that's the first thing we want to do. Identify a pivot starting with the first row and modify the matrix so that pivot is alone in its column. First row, the first non-zero number we encounter is this 1 here. That's the pivot of this row. And before we start looking for other pivots, because we just end up with the 6 and the 5, and that's not very useful, we want to make sure this pivot is alone in its column. So what operation can we do to the second row to get rid of that 6 that's already there? What would get rid of that 6?
You could divide the second row by -1/6 or multiply by -1/6.
Yeah, you could multiply the second row by -1/6. Then this would turn into a -1, and then you could just add the 1 to cancel it out. Or alternatively, you could leave the second row as it is, but add what multiple of the first row?
-6.
Right, we could add -6 times the first row. And either one of those will work. You could modify either one of these rows first by a scalar multiplier and then add. But it often helps to have a standardized process, and the standardized process we often use is instead of multiplying the row we're modifying, we just add a multiple of the other row. And that's not really mandatory. It's just, it's useful to have a standardized method so that you can create a computer program to do it for you, so that it's the same procedure every time. When you're actually working this out by hand, there's many different ways you could approach this to turn it into the final row-reduced echelon form. But it's useful to have a standardized method so as to take all the guesswork out of it. So to do this is the standardized method, usually called Gauss-Jordan elimination. Gauss, or sometimes just Gaussian elimination. The idea is you identify the first row's pivot and use that and that alone to eliminate everything below it. So in this case, that would be modifying the second row by adding -6 times the first row. And let's see what that turns into. First row, we haven't changed at all. Second row, we're taking this 6 and we're adding -6 times 1. In other words, 6 plus -6, so that's 0. Next step, we've got a 6 and we're adding -6 times 4. So 6 plus -24, which would be -18. Then -3 plus -6 times -3, that means we're adding +18. -3 plus 18 would be 15. And then 6 plus -6 times -13, that's positive 78, I think. Plus 6 would be positive 84. So this is our new modified second row. And the numbers sometimes get kind of cumbersome, but the important thing is we have a 0 here because we're trying to eliminate everything in the same column as the pivot. We want the pivot to be alone in its column. Any questions on that row so far? Here's to the next row.
Oh, question?
Yeah, go ahead.
Can you re-explain what makes it the Gauss-Jordan elimination?
Gauss-Jordan elimination is just the standardized process for row reducing the matrix. You take a look, you identify the pivot from the first row, the first non-zero number you encounter, which should be in the top left. If the top left number happens to be a 0, usually you want to start by rearranging rows so the top left number is non-zero. So top left number, as long as it's non-zero, that's your pivot, your first pivot. You want to use that to eliminate everything else in that column. Like we see this 6 here, so we ask ourselves, what do we multiply this by to turn it into -6? Specifically, 1 times -6 will do it. So we take the entire second row exactly as is, and we modify it by adding -6 times the first row. That guarantees canceling out this number because we want the pivot to be alone in its column. And it also modifies the rest of the row along with it.
Gotcha.
So
Thank you.
that's in the Gauss-Jordan elimination, the process of using the pivot as a tool to eliminate everything else in the column.
Okay. Thank you.
And again, there's many different methods of doing this, many different ways to get to reduced row echelon form, the goal. But Gauss-Jordan elimination is just one standardized method of doing it to take all the guesswork out of it. Partly so that you don't have to worry about, well, what should I do next? It's just the standardized process. But also partly because it's useful if you're setting up a computer program to do this, to solve systems of equations in general. You don't want to have the computer stop and make decisions. You want the computer to just follow this list of instructions over and over again until it's done. So the list of instructions is going to include identify the pivot, use that pivot to eliminate everything else in the column, no matter what it happens to be. And next, we also want to get rid of this 5. And since we're still using the same pivot, we're just adding row 1 to another row. We can do this in the same step. We can modify the third row by adding specifically what multiple of the first row would we use here?
-5.
Yeah, if we add -5 times row 1 to row 3, then that 5 will cancel out. So let's see what we get here. And by the way, if you're having trouble keeping track of which numbers are added to which other numbers, I find it can often be useful to write out on the side an extra copy of just that row. If we just write out a copy of row 1, row 1 equals 1, 4, -3, -13. And then write out a copy of -5 times row 1, just for reference. -5 times row 1 would be -5 times 1, -5 times 4, -5 times -3, -5 times -13. So -5 times row 1 is this row, -5, -20, 15, 65. So we're adding this row. It might even help to just imagine picking up this row, -5 times row 1, and overlaying it on top of row 3. Or even just writing it in. This -5 gets added to the 5 here. This 1 gets a -20 added to it. This 1 gets a 15 added to it. This 2 gets a 65 added to it. So those are the values we're adding to each piece of row 3. Or once you get used to it, you could just write it as, or think of it as 5 plus -5 times 1, 1 plus -5 times 4, 1 plus -5 times -3, and so on. But feel free to write out as much or as little as you need to make sure you get this step correct. So let's say we use this approach, 5 plus -5, 1 plus -20, 1 plus 15, 2 plus 65. Any questions on that so far? All right, so let's take a look at our next step. First of all, this pivot, is now completely alone in its column. So we are essentially done with the entire first column. The first column is not going to need any more changes. But if you take a look at the next row, what's our pivot in the next row?
-18.
Yeah, our pivot is this -18 here, which means we're going to need to use that pivot to eliminate everything above and below. And to do that, we're going to need to use multiples of -18 to cancel out the 4 and the -19. That can be kind of cumbersome. Since, for instance, you're going to have to multiply 18 by something to turn it into 19. And that's going to involve some somewhat cumbersome fractions. But we can simplify this a little bit. This isn't strictly speaking part of Gauss-Jordan elimination. It's not really necessary, but it's often useful to make the numbers easier to work with. What do you notice about all the numbers in row 2? Yeah, these are all multiples of 3, right? Since these are all multiples of 3, one thing we can do to make things easier here is to multiply that entire row by 1/3. We can divide out that 3. Again, not strictly necessary, but something useful to watch for, just to make the numbers easier to work with. So let's multiply this entire row by 1/3 and see what we get. And I'm going to erase these steps that we wrote down here just to clear out some room because I've got limited space here. But in general, when you're doing work on this yourself, I would recommend keeping track of all these steps you took. Actually write down the steps and keep track of those, because it's often very useful to be able to refer back to all the steps you took and keep a list of those. I'm just erasing them here to clear out some more space. Let's see what this looks like. First row, we still haven't changed. Second row, we've got 1/3 of 0, 1/3 of -18, 1/3 of 15, 1/3 of 84 is, I think, 18. Yeah, that seems right. And then third row, unfortunately, it doesn't look like there's any common multiples here, so we just have to leave it as it is. So let's see what we can do here. We now have this -6. We want to use that -6 to eliminate the 4. And we're going to have to do a little preliminary arithmetic here. We've got a -6. We want to multiply it by something so that it will cancel out the 4. In other words, we want to get a -4 as a result. What multiplier will make that happen? What can we multiply -6 by to turn it into -4?
Is it 2/3?
Yeah, 2/3 should work, because 2/3 of -6 is -4. So what we're going to do to row 1, we're going to modify row 1 by adding 2/3 of row 2. That way, the -6 times 2/3 is -4, which will add to the +4 and cancel it out. So let's see what that looks like. So we've got 1, and we're adding 2/3 of 0. That's still 1. We've got 4, we're adding 2/3 of -6. That's -4, so it cancels out the +4. We've got a -3, and we're adding 2/3 of 5. -3 plus 2/3 of 5. 2/3 of 5 would be 10/3. And we'll probably want to write the -3 in thirds also, so -9/3. And we end up with 1/3. And then the -13, we're adding 2/3 of 18. What's 2/3 of 18?
12?
So we add 12 to the -13 and we get -1. So there's our new first row. Not too bad other than the 1/3. Second row, we're not changing in this step, so we just leave it as it is. 0, -6, 5, 18. And then third row, we're going to have to use the -6 to modify the -19. So we're going to have to choose what multiplier to use. We have a -6 that we are using as our tool. We want to multiply it by something to turn it into +19 to cancel out the -19. So what multiplier, and of course this is going to have to be a fraction because 19 is not an easy multiple of 6. What fractional multiplier will turn a -6 into a +19?
It's just -19/6.
Yeah, because we want to cancel out the 6. We want to introduce a 19. We also want to change the sign, so -19/6 will work. So that means we're going to have to modify row 3 by adding -19/6 times row 2.
I have a quick clarification. So when we divided by 3 to simplify the second row, isn't 84 divided by 328, not 18?
Yes, it is. Thank you. 28, which means we're going to need to have to change that number as well. And this is something you got to be very careful about when you're doing any operations involving row reduction, because one single arithmetic mistake early on is going to throw off everything from that point onwards. So be very careful about those arithmetic errors. So let's correct that. This should be 28, which means when we add 2/3 of that, 2/3 of 28, that is not a multiple of 3. So we get 56/3. We're adding 56/3 to the -13. So -13 plus 56/3. 13 is 39/3. So that'll be -39/3 plus 56/3. That's 17, I believe. So 17/3 is what we get there. So 17/3. Okay, so that's our corrected new first row. And then the second row, we're not changing in this step. And that means we just need to modify the third row and we know what operation we're doing to it.
Before we get there, is the 18 supposed to be a 28? No, right under the 17 over 3. 0, -6, 5, 28.
And the one we're like working on right now.
Yeah, right under 17 over 3.
The 67 here?
Lower there. Yeah.
Yes, that is 28 also. Okay, anything else we need to modify before we move on? All right, so the new third row, we've got 0 plus -19/6 of 0 is still 0. That's one of the really nice things about establishing some zeros early on. Any zeros you can establish in the first column means that that 0 is not changing the zeros you've already created. In general, if you created a 0 in one of the early columns, you want to keep that 0. You don't want to undo the work you've already accomplished. So using this row as a tool means that this 0 doesn't modify what we already have. But the -19 is going to turn into 0 because we're adding -6 times -19 over 6. Those just cancel out. So we're taking -19 plus 19. And then we now have 16 plus -19 6 times 5. That one we'll probably want to write out. 16 plus -19 6 times 5. That's -19 times 5 would be 95. -95 over 6. And then 16 in terms of sixths would be 96. Does that look about right so far? So that'll just be positive 1/6. And then we also have a 67. We're adding -19 6 times 28. (67) plus -19 6 times 28. And 28 and 6 are both even numbers, so we may as well reduce that fraction first at least. 14 and 3. And 14 times 19 is going to be 280, 270, 266. And 67, we also want to convert to thirds, so that'll be 100, 201, is that right? Anybody want to check my numbers there? I'm thinking this should work out to -65 thirds.
That's what I'm getting as well.
Look okay?
Mm.
All right, so -65 thirds. That seems reasonable. All right, so we now are done with this column. We've eliminated everything above and below the pivot. The pivot, we eventually want to turn the pivot into a 1. We want every pivot to be a 1 and alone in its column. But we can always turn the pivot into a 1 as the last step. At the very end, we can just take this entire row and multiply by -1/6 to turn the -6 into a 1. So turning the pivots into a 1 isn't really super important yet. We can always do that in the very end. But we now have this pivot is alone in its column. This pivot is alone in its column. And what's our next pivot?
Is it the 1/6?
Yeah. In the final row, you go from left to right. The first non-zero you encounter is the 1/6. So that's our pivot. So we're going to want to make that alone in its column also. We'll want to eliminate everything above and below. Well, there's nothing below, so just everything above. Before we do that, though, one thing we can do to make this a little easier, how could we clear out all the denominators, all the fractions in this row?
Just multiply by 6.
Yeah, so let's multiply this entire row by 6. Again, not strictly necessary, but it's going to make the numbers easier to work with. Multiplying by the least common denominator of that entire row. So you're at least dealing with whole numbers. That way we get,
Should we do that with the top row as well because it also has fractions?
yeah, let's go ahead and do that. We may as well multiply top row by 3. And we're going to need to divide it by 3 later because we'll want the pivot to be a 1 eventually. But in between, we can use whatever steps we want. So yeah, let's go ahead and multiply the top row by 3. We get 3, 0, 1, 17. And in fact, it's possible to do that in earlier steps as well. If you wanted to, like if you're having trouble figuring out how to multiply the 6 by something to get the 19 to cancel out, one thing you could do is multiply the second row by 19 and multiply the bottom row by 6. That'll make these become the same value. So you just have to add the opposite of one row to the other row. So using clever multiplication by scalars can make this much easier to see what's going on. Again, not strictly necessary, but it can make the numbers easier to work with. And then third row, we're multiplying everything by 6. So 1/6 becomes 1. And the 3 and 6 reduce to 2. So we get negative 65 times 2 is 130. And that last row tells us something very important. If you reread this last row now as an equation, what would that equation look like?
It just tells us that z is -130.
Right, because you got 0x plus 0y plus 1z equals -130. So we know z is -130. If you wanted to, you could then proceed from there by back substitution. You could rewrite the second row as an equation, -6y plus 5 times -130 equals 28, and then solve for y. Then rewrite the first equation or first row as an equation, plug in your y and z values and solve for x. So it's possible to turn it back into an equation at this point and solve by back substitution. And back substitution in the sense of substituting the final value back into the earlier rows. But we could also take a couple more steps in matrix form to get it all the way to the solution in that format. For example, we now have this pivot. We want to eliminate everything in the same column. How would we eliminate this 1 here?
Just subtract the third row from the first row.
Yeah, subtract the third row from the first row, or alternatively, you could write it as adding negative third row. And in the same step, how could we eliminate this 5?
Just add the third row times -5.
And that should finish up the row reduction. So let's see what we get there. First row, we got 3 plus nothing, 0 plus nothing. That's convenient. The zeros we've already established don't modify anything. 1 plus -1 cancels out. 17 plus -130 is going to be positive 173. No, that's not right. 17, 130, 147?
Yeah.
That looks about right. And then second row, we're modifying by adding -5 times row 3. So nothing plus nothing, -6 plus nothing, 5 plus -5 cancels out, as it should. And then 28 plus -5 times -130, that's 500, 650, plus 28 is 678. And then third row, we can just leave as it is. So we now have every pivot is alone in its column. Ideally, though, we want the pivots to all be what number?
All be 1.
Yeah. So we can do that by just multiplying rows by 1 over whatever we need to. First row, let's just multiply by 1/3. 3 becomes 1. And 147 divided by 3, I believe, is 49. And likewise, second row, we can just divide by -6. -6 divided by -6 is 1. 678 divided by -6 is 100 something, right? 113? 12, yeah, -113, I believe. So this is now what we would call reduced row echelon form. Reduced row echelon form means every pivot is a 1, every pivot is alone in its column. The pivots are in order from top left to bottom right, which doesn't necessarily have to be on the main diagonal, it just has to be in order. And if there are any rows that are all zeros, those rows are all at the bottom. So reduced row echelon form, we can now just read the answers directly off the column. First row, we translate as x plus nothing equals 49. Second row, we could translate as y plus nothing equals -113. And we already know that z is -130. So this should be the solution, the only solution to this original system of equations. Any questions on that so far? So that's the general idea of using an augmented matrix and elimination to solve a system of equations. Write the original system of equations in augmented matrix format, using place value instead of letters to keep track of which coefficients match with which variables. And then follow through this systematic process of using a row to eliminate pivots in all the other rows, or eliminate everything above and below that pivot. Here's a pivot, use that row to eliminate everything in the same column. Here's another pivot, use that row to eliminate everything in the same column. Here is our final pivot, use that to eliminate everything in the same column. And as needed, fill in extra multipliers or divisors to make things easier to work with. Once you've got to reduced row echelon form, turn each row back into an equation and see what you've got. Any other questions on that so far?
Yeah, I have a question. So it seems like you can kind of do anything to a row, a matrix, as long as you're doing it to the whole row. And is that just because we're treating each row as one equation, or is that true for all matrices?
I mean, that is how we define row operations, but it's specifically meant to imitate what we could do to these equations. For instance, one of the first things we did, like, let's say we multiplied an equation, multiplied everything in a row by 6. That would be like if you just multiply this value by 6 and multiply this value by 6 and multiply this value by 6 and multiply this value by 6. All you're doing is multiplying both sides of the equation by 6. So multiplying an entire row by a scalar is equivalent to multiplying both sides of the equation by a scalar. Or if you're interchanging two rows, that's just equivalent to writing these equations in a different order. But the order the equations are written in doesn't matter. Or adding a row to another row, that's equivalent to like adding x to 6x, adding 4y to 6y, adding -3z to -3z, and on the other side of the equation, adding -13 to 6. So each one of these steps, each one of these row operations is just an imitation in different notation of all the steps you can take with a system of equations using the traditional high school algebra methods anyway. It literally is just a different notation for the exact same process. But by using this different notation, it makes it easier to streamline and standardize the process to take all the guesswork out of it. Any other questions on that so far?
I have a quick question.
Mhm.
So I wanted to ask, I guess, with all those like equations, the thing that confuses me is that in like high school we learned how to do all of that, just not that way, right? And then in the lectures, he had some examples, you know, like you can solve it with the upper triangles, or you can solve it like the way you did. And like it seems like there's just a lot of ways to solve the same thing. And there's also like really much easier ways to solve the same thing that just took, you know, a bunch of time. You can solve it like very quickly in a different way.
Yeah.
On exams, like, are we going to be like told do this exact method?
I'm not entirely sure. Again, that tends to vary from instructor to instructor. Some say use this method to solve this system of equations. Others just say solve this system of equations by whatever method you want. So you might want to ask your instructor about that. But in general, it's useful to have a variety of different methods to use, because there are some cases where one method works really easily and the other methods would take a very long time. For instance, if you're dealing with just a system of like 2 equations, 2 unknowns, I would probably just use the high school methods. That would probably be
Right.
much faster. Because this, for instance, takes a long time to set up in the first place and involves an awful lot.
Right.
But if you were dealing with like a system of 10 equations, 10 unknowns, then using the high school methods would be a huge mess, and it would be very difficult to keep track of everything. But the augmented matrix approach makes it very standardized and very organized, I guess I would say. And also there are computer programs for doing this. So you can use MATLAB, or even most graphing calculators have matrix tools that you can use. Like one thing you could do here is just type in this matrix exactly as written into a graphing calculator, and then just hit the row reduce button. Let me show you what that would look like on a TI-84, for
I
instance.
guess I was just wondering, like all of those things, kind of doing the same thing, but it's kind of like preparing us for having more complex problems. That's
Sure, yeah.
cool.
Because the row reduction stuff, you can use it to solve systems of equations, but it can also be used to find out more information about a matrix as well. For instance, finding the inverse of a matrix, one way to do that, the usual way to do that, I would say, is involving an augmented matrix row reduction approach too.
Okay.
But whatever MATLAB or other tool or graphing calculator or whatever you're going to be using, I would recommend taking some time to make yourself familiar with the matrix commands. How to enter a matrix into the calculator or computer. And if there's a tool for just instantly row reducing, like on this one, I can just use the, where is it? Math, row reduce. I typed in this matrix earlier. I can just type row reduce matrix A, and it immediately prints out the values. So this is, from my personal experience, this is the fastest way I have to solve a system of equations. If I have a system of equations and I just need a solution now, I would just type it into the graphing calculator and hit row reduce echelon form. So that's a very fast way to get the solution to the system of equations. And the calculator or computer is doing that by a standardized method like Gauss-Jordan elimination.
Okay. Yeah, I guess I was just wondering about that. So, when you say, okay, so I'm also confused, I guess, on the phrases, if I can ask about that real quick.
Yeah.
So when you say row elimination, you just mean making those rows like the entries, except the entries that you want to stay a number, you're making the rest of the entries 0. And when you say elimination, like all those phrases kind of sound the same to me. And I mean, conceptually, I understand how to solve like the systems of equations. I guess just all those stuff.
Yeah, ultimately, I would say the important thing is knowing how to do it and what to do with these operations. But having the terminology is also very useful in terms of being able to discuss it with somebody else, to be able to describe what you're doing. So for instance, if you're adding a row to another row or multiplying a row by a scalar or swapping rows around, I would call those row operations. Overall, what we're doing is row elimination in the sense that we're using row operations to eliminate some numbers, like canceling out the 6, canceling out the 5. The overall process, the standardized process, is called Gauss-Jordan elimination. And the final result we're looking for is reduced row echelon form.
Okay. Okay, that makes more clear how all the phrases are being used. Cool.
Yeah.
Thank you.
And linear algebra does introduce a whole bunch of new terminology just because it's discussing so many ideas that don't really show up or that show up in very limited forms in previous math classes. So anytime you're introducing lots of new ideas, that's going to be associated with lots of new terminology. So as these new terms get introduced, it might even be helpful to just write up your own personal glossary, just a list of all the new terminology you hear, and then next to it, write out the definition or some examples. So you have something you go back to look up stuff.
Yeah, for sure. Thank you.
And also one of the other really useful things about the augmented matrix approach in general is that the final result is useful even if it doesn't have a solution. For if you're using other methods, if the system does not have a solution or if it has many solutions, all you get is this has no solution or this has many solutions. But with the augmented matrix approach, if the final result is many solutions, you can use that reduced row echelon form to get more information about those many solutions. For instance, to be able to write out the general solution, and even going back to the idea of writing a line parametrically. Like let's say you've got some planes that intersect along an edge, along a line. You can write out an equation of that line using the final reduced row echelon form. So there's many ways you can get more information about that final result, even if there's no solution or no unique solution. Any other questions on that?
Yeah, one more. So what we did is that we tried to like simplify like the augmented matrix to get the reduced row echelon form, correct? And what was the other type of form and what was the use for it?
Upper triangular form.
Yeah, I think that was that one.
Yeah.
What?
For reduced row echelon form, you want to cancel out everything above and below all the pivots. Upper triangular form means you're just canceling out everything below the pivots and you're leaving everything above the pivots exactly as it is.
Okay.
So it's basically almost like going to reduced row echelon form, but skipping some of the steps. You're only looking at canceling out stuff below the pivots. You can ignore what's above the pivots.
Okay, gotcha.
And that's mainly useful if you want to solve it using back substitution, because the final row is still going to look like 0, 0, 1, negative 130. But once you've got that, you can write all the other rows as equations, plug in negative 130 for z and solve for y in the second equation, then plug in y and z in the first equation and solve for x. So that would be solving by back substitution. They both lead to the same result. It's just a difference of, do you want to partially do this with augmented matrices and then do the rest with the equations? Or do you want to do the whole thing with augmented matrices and jump straight to the solution at the end?
Okay, gotcha.
They start the same way, but the way you finish it off is two slightly different approaches.
Cool.
Any other questions on that? All right, that's it for today. Feel free to email me if you have any other questions or if you want to request any examples for next time, and I will see you next week.